Now that we have a good handle on Fourier transforms, let's consider some interesting application of Fourier transforms in image processing. There's a Colab notebook that goes along with this lesson, and the link will be provided in the video, in the description of the video. Remember, the whole purpose of this journey into Fourier transforms is that there are things that we can do more easily and efficiently in the frequency domain than we can do in the spatial domain. And one of the classic examples of that is presented in the Fourier convolution theorem. This theorem states that the transform of the convolution of two functions is equal to the pointwise product of the Fourier transforms of each. So let's say I have an image G and a kernel H, and I do a convolution of them and then take the Fourier transform of that. That is the same as taking the Fourier transform of the image, taking the Fourier transform of the kernel, and then doing a pointwise multiplication. Now, the corollary of that is if you take the inverse Fourier transform of both sides of this equation, you end up with this, which says that instead of doing a convolution of the image and kernel in the spatial domain, we can first take the Fourier of the image, the Fourier of the kernel, do a pointwise multiplication, and then take the inverse Fourier of that, and we will end up with the same result. So what this is saying is that convolution in the spatial domain is equivalent to multiplication in the frequency domain, and there are many instances in which multiplication in the frequency domain is much faster and more efficient than convolution. So let's test this for ourselves and see if it is in fact true. So here I've created a 5 by 5 image using just random integers. I've created a 3 by 3 kernel. This is a Sobel kernel. And I use SciPy's Convolve 2D to do the convolution with the mode same and with zero padding. So let's save this. This is our convolved or filtered image. Let's see if we can do the same in the frequency domain by multiplication. The first thing we think about is that in order to be able to do pointwise multiplication, both of our arrays must be the same size. That is, the kernel and the image must be the same size. And there's a wrong way to do this and a right way to do it. I'm going to show you the wrong way first. We'll say, well, we can simply zero pad the kernel to be the same shape as the larger array, which is our image. So let's do that. We take the shape of the image, the shape of the kernel, we subtract them, divide by 2, that's our padding size. We pad our kernel to that size with zero padding. And then we assert that the shape of our padded kernel is the same as the shape of our image, and we will pass this assertion. Now that we have our image and padded kernel, we simply take the Fourier transform of the image. Here I'm using the NumPy's two-dimensional fast Fourier transform. We have many options for this, but NumPy is easier for this application. And I'll do the same with the padded kernel. I take its Fourier transform, and now I have the Fourier transform of both. I do a pointwise multiplication of the Fourier transforms. I take the inverse Fourier transform of the product, and I take the real component of that. That's our result. And if we've done everything right, this result should be the same as our convolution in the spatial domain. But when we actually print it out, we see that they're not the same. This gives false. And the reason they're not the same is because we did the padding wrong. The correct padding rule is this. If we have an image of size m by n and a kernel of size little m by little n, then we have to zero pad both of them to this common size. Okay, So let's do that and see if it works. So our desired shape is, this is m plus little m minus 1. This is n plus little n minus 1. We pad both the image and the kernel to that common shape. This is a little shortcut here. NumPy's two-dimensional fast Fourier transform can zero pad the image and the kernel to the desired shape and take its Fourier transform at the same time. So we're saving steps here. Now we end up with our forward Fourier transforms. We do the pointwise multiplication. We take the inverse transform and we take the real component of that. Now we have ended up with our proper convolution. But remember, now we have, this is of a size that's bigger than both our image and our kernel, so we have to crop it to the size of the image, and this is the simple cropping code. Now if we compare our results here to the spatial convolution, we'll see that the spatial convolution in the spatial domain gives us this. The convolution in the frequency domain by multiplication gives us this, and they're identical. So the question is, which is faster, spatial domain convolution or frequency domain multiplication? Well, the time complexity of this is O of mn times little m little n. And the time complexity of frequency domain multiplication is the following. First, we have to take the fast Fourier transform of the image. That's mn log mn because we're using the fast Fourier transform. We have to do the same with the zero padded kernel. That's again mn log mn. We do the pointwise multiplication. That's mn, and we take the inverse fast Fourier transform. That's again mn log mn. All of these are in the order of mn log mn together. When the kernel is very tiny, like a 3 by 3 or 5 by 5 kernel, this basically becomes negligible and we end up with a time complexity of OMN. But when the kernel is large, then this becomes quite intractable and the Fourier method becomes much faster. And here's an example of that. For the same image, 512 by 512, if we use a small kernel, the spatial convolution method wins. But if we use a larger kernel, 31 by 31, the Fourier transform method wins. And if we have a much larger kernel, the fast Fourier transform method is much, much faster. So let's consider a related application. Remember, in Poisson image blending, we reach a step where we have B, which is the known Laplacian of our source image, and we have F, which is the unknown blended pixel values in the max that we're trying to compute, and we have delta, which is our Laplacian operator. And we're trying to compute F, and we go through this big exercise of first linearizing F into a column vector, and then constructing a matrix A, which is a sparse matrix of size n by n, that's composed only of 4s and -1s and mostly 0s, and this basically encodes our Laplacian convolution. So now the problem is reduced to A times F equals B. We know A, we know B, and we can compute F by inverting the matrix A. And this is the classical Poisson method. It turns out, though, that inverting a matrix A is quite computationally expensive. And even though it's a sparse matrix, and even though we have Python libraries that do it for us, it's still expensive. So let's see if Fourier transforms can help us here. Instead of inverting the matrix, we go back to this equation, AF equals B, and we take the Fourier transform of both sides. Now this, it turns out, reduces to this. This lambda kx ky is a diagonal matrix. It turns out that the matrix A that we constructed here has properties that allow it to become diagonalized in the Fourier space. And we can easily compute this diagonal matrix, as I'll show you here, and then multiply it by the Fourier of f to get the Fourier of b. So the way you compute the diagonal matrix is that for every horizontal index x and vertical index ky, you populate this matrix with the value of this function. So now that you have the diagonal matrix, you can very easily solve for f by simply dividing the Fourier of b by the diagonal matrix and taking the inverse of that. So this problem is solved in this fashion. And what we have done is that we have avoided inversion, matrix inversion, and have transformed the problem to a simple division problem in the Fourier space. So in assignment 3, you will do exactly that. You will use the Fourier convolution theorem to implement Poisson image blending in the Fourier space using this formula and avoiding matrix inversion.